And so basically, let's say if in one instant, this is just in one instant of time. In one instant of time, all the electrons are over here on the left, then we're going to build up negative charge on the left, and we're going to have positive charge on the right. What this is going to do is it's going to create a dipole, a negative pole and a positive pole. But is that dipole permanent? No. That dipole is very short-lived because this is not going to be a sustainable situation. It's like this. Let's say we create a wave in our pool. Is that wave going to stay there forever? Or eventually is the pool going to settle back down and be uniformly? Yeah, eventually. So we created a wave here, and eventually, in the next instant of time, it's gone. But when this wave is here, what's that going to do is it's going to do something. And so this is what we call an instantaneous dipole. Instantaneous dipole. Now, if there's another carbon atom nearby, then this carbon atom has 6 electrons, and those 6 electrons are going to say, hey, there's positive charge over here. If there's positive charge over here on the left, then the electrons are going to migrate to the left to maximize their interaction with the positive charge over here. And so what that's going to do is it's going to induce a dipole in an adjacent atom. So it's going to cause the adjacent atom's electrons to be polarized. Just like this wave here will cause the water around it to deform or to change in some way. And so this is called the induced dipole. And so our book calls it an induced dipole attraction. And so for one moment, we got this wave. For one moment, we have this attraction. And this attraction is going to be an IMF. It's not a bond, but it's just a momentary attraction between 2 carbon atoms here. And it's going to quickly die like this wave. It's going to quickly die, but for that moment, there was an attraction. But the situation is there's so many carbon atoms that, in the next instant of time, there's another attraction, then another attraction. So net, we're going to have these carbon atoms held together by these instantaneous induced dipoles. And so that's what's going to keep the liquid a liquid. Okay, then as we continue to heat this, it's going to vaporize this, and so we'll get vaporized carbon atoms. So just gaseous carbon atoms here. Gaseous state. We're going to completely break these attractions holding them together. All right, so they're going to have high melting points. Now, is water going to be attracted to this? Now, water is very polar. So are diamonds water soluble? No, water is not going to be attracted to this. The carbon atoms are non-polar. And so these are insoluble, insoluble in water. Not only are they insoluble in water, they're insoluble in other things like oil. Some things are soluble in oil, some things are soluble in water. Well, diamonds are insoluble in both oil and water. They're insoluble in water because water is not attracted to these. Water is attracted to ions. Ions have charge. This is insoluble in oil because the bonds are too strong. There are some ionic compounds where the bonds are too strong. That water can't break it apart, even though it's ionic. And so water sure is attracted to something like calcium carbonate. It sure is attracted to the calcium ions and carbonate ions, but the bonds in calcium carbonate are too strong for water to overcome. However, it's not attracted to this. What else can we say? Are these good conductors of electricity? No. Except for graphite. Graphite's pretty good. And so these are typically non-conductors or insulators. So those are some properties of the solid. So examples of a covalent solid would be, these are all crystalline. You can tell these are crystalline because they have nice crystals here. Quartz, amethyst, citrine, All these have a nicely ordered structure. These are held, the silicons here, the oxygens are here, these are held together by covalent bonds. Covalent bonds are hard to break. So these are going to have a high melting point. Also, they aren't going to be very soluble. In fact, they're insoluble. Quartz. The next type of solid we're going to look at are the metallic solids. Like aluminum metal here. Now, metallic solids, they vary. Metallic solids are held together by metallic bonds. So we had ionic bonds, covalent bonds, now metallic bonds. Metallic bonds we looked at a while back. Metallic bonds are thought to be the cations, like aluminum would be a 3+, and a sea of electrons. So here we have the aluminum cation, and then the electrons are delocalized in this sea. The cations are fixed in position. Delocalized just means spread out, like a fog, water, spread out. So this is called the electron C model of bonding. So what's holding them together is like a covalent bond. You know, we've got these positive charges held together by this cloud of negative charge pulling it together. Some metals have extremely high melting points, like platinum, tungsten, gold. Those are really hard to melt. Some metals are really easy to melt, potassium, cesium, calcium. Those metals are easy to melt. And so the melting point varies from very low to very high, depending on how strong. Metals, are they soluble in water? No, they're insoluble. Like if you're a water molecule, you want charge. When you look at these aluminum atoms are non-polar, not charged. Water is not really going to be pulling on those atoms. Here you see charge though, but so it's insoluble in water. However, we can dissolve aluminum if we have an oxidizer. And so, but it isn't, you know, oxidizers can dissolve metals, but it changes it. It's no longer aluminum metal. We're going to have aluminum cation. Aluminum cation doesn't conduct electricity. And so oxidizers can dissolve chemically, not physically. What else can we say? These are good conductors. Good conductors.